This would be, I don't know, gosh, if you want to trace this back to where this kind of question started, this is a kind of a long time ago kind of a question. I've drawn a graph up here for you, and I'm going to ask you if you could answer this question right here. If I said, we're going to say that this function is f of x, and if I said the limit as x goes to 0 of f of x, based on the graph, what would you say?
1.
Assuming the scale there is 1, 2, 3. You say, from the left we see that behavior. Bless you. From the right we see that behavior. And I agree. Looks like we're headed towards 1, right? But if you take a little closer look up here, can you see the function that produced that graph?
Sine of x over x.
Sine of x over x. So if we tried to do this analytically, like if we said f of x, limit as x goes to 0 of f of x, that would be the limit as x goes to 0 of sine of x over x. And if you think about the way that we typically would at least think about limits, is we just plug in, right? Do a direct substitution. And when you do that, sine of 0, 0, not a big deal. But then over 0, big deal. And so then the question of the moment, and we won't spend our whole class on this, let's spend a little bit on this. Question of the moment is, how could the graph show that, that the limit appears to be approaching 1, yet when we try to do the actual analysis of it, we get something like 0 over 0. How can we get those two things to agree, right? Because right now they seem to be presenting very different answers, and it's math class. We should be able to make these things agree somehow, right? And so that's one of the things we'll be working on today, and in our 8.7 is where we're going to head today. So just a kind of a brief overview of our week. Here is my... we're going to talk about what indeterminate forms are. We'll talk about this L'Hopital guy. Sometimes his name is spelled El Hospital. They put an S between the O and the P. Other times you see it without. So, maybe if you're famous one day, they'll maybe misspell your name too, or be unsure of your name. Who knows? But it's L'Hopital. It's not El Hospital or El Hospital, or I don't know, all the different ways you could say that. It's just L'Hopital.
What ethnicity is he?
I think French, if I remember correctly. And how many people have an apostrophe as an integral part of their name? It's pretty cool, right? Anyway, so you guys probably aware, I think you're probably aware of this, like all the limits that we did, especially in chapter 1, some of the ones we did in chapter 3, they were all, I guess I would say, carefully designed to work, right? If you think back, I don't know if you guys remember this, I'm doing this in Algebra 1 right now. You guys remember when you first learned how to factor, like x squared plus 7x plus 10? And, amazingly enough, pretty much all of them worked, didn't they? They all factored. And so, as a young student, you're just thinking, oh, this is super easy. I can handle all these. But then you start to learn, well, pretty much most of them don't work, right? Most of those quadratics don't work out the way that we would want them to. They don't factor very easily. And so we're going to delve a little bit deeper into some of these other limits that you were kind of protected and sheltered from in chapter 1 because we didn't want to throw everything at you. And we're going to throw a little more of everything at you. These would be some limits that don't work out quite as well as we might hope, and a little way to deal with it. So sometimes, many times, a limit will produce what we call an indeterminate form. An example of such is the one that I just showed you, 0 over 0. So this is called indeterminate, which is sort of a made-up word. I guess somebody mentioned the other day that all words are made up. But this is kind of one of these made-up words that essentially says we don't know the answer yet, right? Based on the evidence we see, we don't quite know what the answer is, and so we might need to do a little more work to get to the answer. So sometimes we're going to use algebra or some other type of manipulation to deal with it. That's what we did in chapter 1. But other times, like now, we won't be able to use nice, convenient algebra. Like if you think about the video, the earlier part of the video we just made, sine of x over x, there's no way to manipulate that. There's no way to be like, oh, well, if we just factor this and cancel that, we're good. There was no option for that. So L'Hopital's rule will help us deal with that. So there are lots of indeterminate forms. We are only going to be focusing on 2 of them. Okay? I've highlighted them up there for you. The 2 indeterminate forms would be 0 over 0 or infinity over infinity. I've highlighted those, but I've listed out some of the other indeterminate forms that are out there, and I'll just briefly go over these. This one right here, I'm underlining it, 0 times infinity is indeterminate. Here's why it's indeterminate. Because we think anything times 0 is 0, right? It's a little bit of a misstatement. Any real number times 0 is 0. But infinity is not a real number, so it doesn't have to follow the rules for real numbers. 0 to the 0 is indeterminate, because that actually leads back to this. It actually leads directly back to 0 over 0. Infinity to the 0, again, we usually in the past have said, hey, anything to the 0 is?
0.
No, 1, except 0 to the 0. Well, we can add another exception to that. Infinity to the 0 is indeterminate as well. You're like, okay, just simply means you can't figure out the answer yet, right? It's a confusing form, or maybe a contradictory form. Here's another one. Everybody loves this one. 1 to the infinity. What does everybody want to say the answer to that is? Well, infinity or 1, right? Because 1 to the infinity, wouldn't that just be 1 times 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 1. And as soon as I stop, think about this, Drew, think about this. As soon as I stop saying times 1, haven't I just violated what that told me to do?
Yeah.
So anytime you say, hey, 1 to the infinity equals 1, that tells me that you stopped multiplying, which is exactly what that's not. That just says keep multiplying by 1. So it's not that the limit wouldn't be approaching 1, perhaps, maybe, or, oh man, Ben, so soon, head up. There we go. It's simply this, that we don't know the answer. If we have time, this might be a Friday thing for us, but if we have time, I might show you one of these, and I'll show you that if you get that form, the answer very definitely might not be 1. It could be something else entirely. So something to think about.
How could that be?
I'll maybe show you on Friday. I promise you it. Very possible. And then lastly, infinity minus infinity. Again, how can you have something that is infinitely huge minus something else that's infinitely huge? You want to say 0, right? But remember, infinity is not a real number, so it doesn't have to follow all those real number rules, such as any number minus itself is 0, because infinity is not a number. So, all of these forms are not figure-outable, they're indeterminate. And so we need to do further analysis to try to figure out what it leads to. It's not saying that there's no answer, it's just saying, we don't know if we know the answer yet. It's a kind of a question mark. But like I said, the only two that we are going to focus on in our class, 0 over 0 or infinity over infinity. That's the stuff you need to be good at. Okay? It's important to note that some expressions might look indeterminate but are not. 1 over infinity, 1 over 0, 0 over infinity. Those look like they kind of fit those forms, but those forms are exact. It's not things that look like them, it's things that are those. And so, if you get 0 over 0, that's indeterminate. 1 over 0 is not indeterminate. 1 over 0 is simply undefined. It means there is no answer. That makes sense? So there's a difference between undefined, not existing, versus indeterminate. Indeterminate just means, we don't know the answer yet. 1 over 0, we know the answer. There is no answer, right? It's not a real number or undefined. That makes sense? So it's kind of a fine hair to split, but split it we will. Okay, so I'm going to show you L'Hopital's rule. I'll attempt to prove to you that L'Hopital's rule is valid. And maybe we'll do an example or not. I don't know. We'll see. But we'll at least get to what L'Hopital's rule is and a little bit about how it works.
Would it involve using
L'Hopital's rule is simply stated right there. The limit as x approaches c of f of x over g of x is equal to the limit as x approaches c of f prime of x over g prime of x. So it doesn't involve any u's, it involves a derivative. So what this is attempting to say to us is that the limit of a quotient, f of x over g of x, is the same thing as the limit of the derivative of the top over the derivative of the bottom. Now this only applies if the conditions for L'Hopital's rule are met, namely 0 over 0 or infinity over infinity. In other words, you cannot use L'Hopital's rule unless those conditions are met. That make sense?
So you first have to plug in first.
Yeah, you got to decide if it actually applies first. And don't just start differentiating stuff. You see the note there. It's important, you guys, to note that this is not the quotient rule. Notice I didn't do low D high minus ID low square of what's below. It's not the quotient rule. It's simply do the derivative of the top, do the derivative of the bottom, and then retry the limit. And then another note down here, L'Hopital's rule can be applied multiple times, 2, 3, 4, 5, 10, 20, 1,000 times. Not that we're going to be doing that. We might do a couple times, as long as each attempt produces that same indeterminate form that we mentioned earlier, either 0 over 0 or infinity over infinity.
Can you use L'Hopital's rule infinitely, or no, it will end?
Should end.
Okay.
I don't know. Maybe there is a case where...
What if it's like just a bunch of sine and cosine functions?
Yeah.
that could be involved.
Just keep going.
Could be that. Yeah, it certainly could be involved. I don't know that that would necessarily make it go on forever, because eventually
Actually, you can skip to the
you're going to do like cosine of 0 or sine of 0 would be 0, but eventually you do cosine of 0, which is 1, which means you're done with L'Hopital's rule. So, yeah. Okay, so let me just show you a brief proof of L'Hopital's rule. So let's say we start off with this. Limit as x approaches a of f of x over g of x. And let's say that as we apply that limit as x approaches a, we try that direct substitution thing. Let's say that that causes us to get 0 over 0 or infinity over infinity. If we get that, we can enact L'Hopital's rule. And here is the proof of it. You don't have to do this whole proof thing. You can just simply do the shortcut with the derivatives, as we know how to do the power rule and all the derivatives of sine and cosine and all that kind of stuff. But here's how it works. I'll do this in a different color. This is in blue, but this is all predicated upon getting those indeterminate forms. So the first thing I'm going to do is a little bit of a weird step, and I'll clarify it here in a second. I'm going to say limit as x approaches a of f of x minus f of a over g of x minus g of a. And for this to work, this is really terrible, terrible math, unless f of a and g of a are both 0. And that's not that much of a stretch, because if we really did get one of those indeterminate forms, like 0 over 0, then perhaps f of a and g of a are both 0. So it's not a big stretch here. But this proof does not work. This is the baby proof, by the way. This proof does not work without this stipulation. So I'm just saying those two things have to be 0 for this to work. Now the next thing is just straight up regular algebra, and I don't need to explain this away. If I divide the top of the fraction and the bottom of the fraction by the same thing, that's always allowed, right? As long as I don't divide by 0. So I'm going to write this as limit as x approaches a, and it's going to be f of x minus f of a. I'm going to divide that by x minus a over g of x minus g of a over x minus a. I've just divided top and bottom by x minus a, right? Okay, so I'm going to do one more thing here. This is something we talked about way at the beginning of the year, so you may or may not remember it perfectly. But here it is. If you have the limit of a fraction, you can rewrite it as the fraction of two limits. So in other words, the limit could apply to the top, and the limit could then be applied to the bottom. So I'm going to rewrite this like this. Limit as x approaches a of the top, so it would be f of x minus f of a over x minus a, all over the limit as x goes to a of g of x minus g of a over x minus a. And believe it or not, we're about to finish this. As long as you can recognize what the top is. I'll put a circle around the top. If you can recognize what that is, and then if you can remember recognize what the bottom is, we'll be done. Do you guys recognize what the top is? Definition of the derivative of f of x, right? Hang on one second. Isn't the denominator the exact same thing except the definition of the derivative of g of x evaluated today? And so that allows us to finish this. Let me just finish this because we're like right there. This would equal then f prime the derivative, right? Like you said, the derivative of f. So f prime of a over g prime of a.
On the bottom part of that last fraction, is that g of a or
That's
g
what
of
I
x?
asked.
Oh, goodness. Let's make that an a. Yep. I think I said it right and wrote it wrong. Should still be g of a. Yeah, thank you. Thank you both for asking. Okay, so if you go back and look at what I proposed L'Hopital's rule to be up here, I said, hey, limit as x approaches c. I used a c instead of an a up there. Of f of x over g of x equals limit as x approaches c of f prime over g prime. Well, then wouldn't this equal f prime of c over g prime of c? Which is exactly what we ended up with down here. So again, this only works, the conditions here are very important for us to understand. This only works if we have one of these two conditions, either 0 over 0 or infinity over infinity. If we get those, then we can apply L'Hopital's rule, reevaluate the limit, and see what we get. We might continue on with L'Hopital's rule if we continue to get indeterminate forms, or we could be done and actually get an answer. So, what do y'all think? Let's do one example. I think there's one example coming up here. Let's do that, and then we'll save the rest for another time. So I want to show you guys some notation. This is not official notation, I suppose, but many folks do use this. It's recognized by a lot of teachers and professors and students alike. So here we go. Number one says limit as x approaches 0 of that thing right there. Let me just encourage you. If this is out of context, right, this is on some random quiz or test, you're not going to know, is L'Hopital's rule a thing that I'm going to be using here? Maybe it is, maybe it isn't. Let's go all the way back to chapter 1. What is potentially the easiest way to evaluate any limit? Just plug in, right? There's not really any solving here because there's no equal sign, but just plug in, right? See what happens. So if I plug in with the 0, I end up with 0 in the top, and then in the denominator, sign of 0 is... So 0 plus 1, that doesn't really matter because it's going to be 0 times that. We get 0 over 0. So I want to say this, that you writing this right here is quite important. It helps a lot, I think, because it tells you kind of where to go next. But it is quite important because what that does right there, that sets the conditions for L'Hopital's rule. That says, hey, I got 0 over 0. That means that I'm allowed to use L'Hopital's rule. If we don't write that, we haven't proven that we've met the conditions for L'Hopital's rule. Make sense? Okay. So once we've said, hey, you know what, 0 over 0, that's one of those indeterminate forms. We can't figure out what it is. We can use L'Hopital's rule. Let me show you what I would prefer you guys to use as a notation that you're going to use L'Hopital's rule. Just draw a little arrow, and on top of the arrow, just write LH, L'Hopital's rule, LH, L apostrophe H, that kind of thing. L'Hopital's rule saying, hey, I'm about to apply this L'Hopital's rule thing and see what happens. So here's what we would do with this one. We would say the limit as x goes to 0. And then we've got to differentiate the numerator and differentiate the denominator. What's the derivative of the numerator?
1.
So what does that tell you right now?
You're not going to do it again.
You're not going to be doing L'Hopital's rule again on this one, right? Because in order to do L'Hopital's rule, that would either need to be a 0 or an infinity. So we know for sure, however this works out in the denominator, we are going to finish right here. We're not going to have to do a second step of L'Hopital's rule. Okay, we've got to do the derivative of the denominator also. Product rule. There we go. Good. So let's try it out. 1. D2 is just 1 plus 2 D1. Stretch that out just a little bit. Okay, so once you've applied L'Hopital's rule, done the derivative of the numerator, done the derivative of the denominator, now we just retry the limit. We try to plug back in. So when you do that, what do you get?
1.
Yeah, we get, and the top is 1, right? Mm-hmm. In the denominator, sign of 0 is still 0, plus, and then it would be 1 times 1, right?
Yeah.
So 0 plus 1 would just give us 1 over 1, or 1. So this is actually kind of similar. It's a little bit different, but it's similar to the graph that I showed you at the start of class. If you ever have questions about this, you're like, man, is this really how it works out? And you've got a calculator available, I would graph it really quick and look at it and be like, hey, does this really seem to be headed towards 1 from the left and the right? The graph should tell you what you need to know if you've got that available to you. But that's just kind of a start with L'Hopital's rule. Does that work? Makes sense? Okay, so we'll pick this up at a later time. But for now, I think I am done.